Hi students, today we will start next unit of this course which is about radiation detectors. Experiments in nuclear and particle physics depend upon the detection of various radiations and particles. For example, recently a Higgs particle, which is also called God's particle, is detected with the Large Hadron Collider at Geneva. Not only in experiments, the detection and measurement of nuclear radiations, such as gamma rays, beta particles, alpha particles, neutrons, and protons, is also of prime importance in the study of radiation dosimetry, radiation protection, radiation therapy, etc. These radiations and particles are so tiny that they cannot be detected by our natural senses. In fact, their detection and measurements have to be carried out by some suitable instruments based on the interaction of these particles with matter. These instruments, working on the principle of interaction of radiation with atomic electrons in the matter, are called radiation detectors. The matter in the detection can be gas, liquid, or even solid. These detectors can be classified according to the detector material, that is, whether it is a gas or a liquid or a solid, and the type of particle to be detected. There are various radiation detectors developed time to time depending upon the requirement. Let us now discuss some important detectors of all time. The first type that we will discuss is gas filled detectors. As the name suggests, a gas filled detector consists of a gas filled in a metallic chamber. There are two electrodes, one is anode and other is cathode. The anode is a thin wire which runs through the center of the chamber. The cathode is simply the metallic surface of the chamber. These electrodes are connected to external circuit consisting of a resistor, a capacitor, and DC voltage. There is a thin window on one circular end of the chamber which allows the particles to enter the chamber. Now, let us discuss the principle of the detector. When the particle to be detected enters the chamber through window, it ionizes many gas molecules, due to which positive ions and electrons are created in chamber. The positive ions move toward cathode because of negative potential at cathode, and electrons are collected at anode as anode is provided positive potential. Due to collection of electrons at anode, the potential at anode drops. This drop in potential generates an electrical signal. This signal is sent to a counter which records this signal as the detection of particle. Hence, whenever a particle enters the chamber, it ionizes the gas. The electrons of produced in ionization are collected at anode to produce a pulse. This pulse results in the detection of the particle. The working of gas field detector depends upon the amount of voltage provided to the electrodes. The detector behaves differently at different voltages. We can divide the characteristics of detector in different regions, which we will discuss further. The working of gas field detectors can be divided into 6 different regions, as you can see in this figure. These are recombination region, ionization region, proportional region, limited proportional region, the Geiger-Müller region, and continuous discharge region. In recombination region, voltage is varied from V0 to V1. In ionization region, voltage is varied from V1 to V2. In proportional region, voltage is varied from V2 to V3. The limited proportional region occurs at voltage between V3 and V4. The Geiger-Müller region is obtained at voltage varying from V4 to V5. Continuous discharge region is obtained at voltage more than V5. In this figure, you can also see two curves, one for an alpha particle, the upper one, and other for a beta particle, the lower one. The pulse height for alpha particle is higher than for beta particles because alpha particle, due to its higher charge than beta particle, causes more ionizations of the gas molecules than beta particle. Now let us study these regions one by one. The recombination region starts from zero applied voltage across the electrodes. When there is no electric potential at electrodes, all electrons and positive ions created by the incident particle in the gas recombine to form neutral molecules back again. So electrodes have no charge to collect and therefore no pulse is produced. When the applied voltage is increased by a small amount, electrodes get some potential. Now some of the ions and electrons manage to reach the electrodes and a small pulse height is formed, while most of the ions and electrons still recombine. As the voltage is further increased, recombination decreases and ions collection at electrodes increases. Hence a rise in pulse height is observed. Ionization region starts at voltage V1. At this voltage, potential on electrodes is so high that all primary ions produced by incident particle are collected and therefore there is no recombination. If the voltage is increased beyond V1, there is no rise in pulse because the electrodes, even they are at higher potential, but have same number of primary ions to collect. Therefore, the pulse height is constant in this region. But pulse height for alpha particle remains higher than for beta particle because the number of ions produced by alpha particle for the same voltage is greater than those produced by beta particle. Next is proportional region, which starts from voltage V2. At this voltage, the potential at electrodes is so high that now primary electrons, that is electrons produced by incident particle, are strongly accelerated towards central anode and therefore they obtain enough kinetic energy that they cause further gas ionization called secondary ionization. As a result, the number of ions starts multiplying and pulse height rises once again. At higher voltage, the secondary electrons in turn cause tertiary ionization and so on, and hence pulse height keeps rising with increase in voltage. In this figure, you can see primary electron produces its own bunch of electrons, which is called avalanche. The number of ions so formed increases exponentially with the applied voltage, and this process is called gas multiplication. It is described as total number of ions formed by secondary ionization divided by total number of ions produced by primary ionization. The gas amplification is proportional to the number of primary ions created by the incident particle. Hence, the curve for alpha and beta particles are parallel, as alpha particles are capable of producing more primary ions. For this reason, the gas-filled detectors operating in this region are called proportional counters and are used to measure particle intensity and its energy. In limited proportional region, the proportionality is lost, though multiplication of electrons and ions still increases. The electrode's potential in this region is very high, due to which primary electrons are fast accelerated towards anode and hence gain kinetic energy in a very short distance to cause secondary ionization. Secondary ionization also cause tertiary ionization in short distance. So there are chances that different avalanches interfere with each other. Now, more the primary ions, the larger the numbers of avalanches, and hence the more are the chances of interference between various avalanches. As the growth of one avalanche tries to prevent the growth of other avalanches, ions produced by alpha particles, which are more in number, therefore will increase slowly with increasing voltage than the net number of ions produced by beta particles. Therefore, the two curves will converge at V4. The Geiger-Müller region, the total number of ions produced is independent of the number of primary ions produced, and hence the pulse height is independent of the type and energy of the incident particle. As you can see, both alpha and beta particles have the same pulse height. The gas-filled detectors operating in this region are called Geiger-Müller counters, which are named after the physicists who have developed this detector. In continuous discharge region, the voltage is so high that positive ions of gas molecules are so strongly move and bombard the cathode that they pull electrons from cathode, such that when these electrons are attracted by positive ions, UV photons are produced. These photons themselves interact with cathode surface or gas and produce photoelectrons. These photoelectrons cause further ionization, so a continuous cycle of ionization and discharge with higher pulse height takes place. In the next lecture, we will discuss various detectors which have been designed out of these voltage versus pulse regions.